Hey everybody, today what we're going to work on, you can see the title up at the top of the screen. We are going to work on translating problems, and I'll call today translating problems 1 because today is the first of 2 days that we're going to do this. When I mean translating problems, really what we're going to do is we're going to take a problem in an English language situation and we're going to turn that, for the purpose of a solution, into algebra. I am assuming that when you walk into this video, you are good on your mechanics. That is, if you create a system, you can solve it. If you create a quadratic equation or a function, you can solve it or manipulate it to whatever you need. That is, the mechanics are up to speed. You are comfortable with it all. So if we get to a point where you're looking at it and you're going, the mechanics are not where they need to be, my strongest recommendation is to go back and work through those mechanics. We are not doing that today. We're going to finish the problem when we get to a point of algebra and make the assumption that you would be good to actually finish it to solve the question asked. Okay, with that being said, let's jump into the first problem. So the first problem says the sum of two numbers is 13 and their product is 42. Find the numbers. Now, I'm going to walk you through the process for this one, and I'm going to tackle it two different ways. I am not saying that these are equal, and I want to be very clear on that. There's kind of one way where I'm going to shut my brain off early and it's going to require more work afterwards. Or I'm going to have my brain going a little bit early, which means I'm going to have less work to do afterwards. Okay, I think the second way we go through this is going to be the better way. So hang tight as we're going through the first way if you would not solve it this way. Okay, let's jump in. The question says the sum of two numbers is 13 and their product is 42. Find the numbers. Well, a starting point can always be, if you're looking for numbers, then allow those numbers to be represented by variables. So you could say that you were going to and let's just say that I used x as a generic variable. Let x, and I am fine if you just want to use the word rep for represent, let x represent the first number. And then what you could say is that you were going to let y represent the second number. Now, I want you to notice, I said at the beginning, two different ways to solve this. That I'm going to argue you didn't do much thought to solve the problem this way. But if the question says find two numbers or find the numbers, then you could allow x and y to represent those numbers and begin a process. Now, the problem is because you have two variables, you are going to have to solve for both of those variables, which might mean a little extra work. Okay, what I'm going to do is I'm going to put a little wavy line down on my page, and I want you to do the same. You can see the approximate spacing for where I put that line. I would argue I think you should try to match up with my spacing. Okay, I'm going to continue to solve the purple problem, or I should say the problem with the purple method. If that's the case, then what I can do is I can take my two sentences and I can translate them, or my one sentence in the first part. The first part of that sentence said the sum of two numbers is 13. Well, if x and y are my two numbers, then sum means add. If I add them together, that gives me 13. There is an equation. The problem, of course, that equation has two variables, so it doesn't allow me to solve for either one of those variables. But the second half of that sentence says their product is 42. Product means multiply, and so you could say that x times y equals 42. And there you go. What you have, two equations, they both contain the same variables. Therefore, you have a system of equations, and you could, of course, solve. Now, as I mentioned, we're not solving this problem for today. I assume that if you had that purple system, you would be good to go. So can we just say, for the purpose of today's topic, your next line in the problem would be a little star, and you would just write that you were going to solve the system. Just as a little note to yourself of what you would do next if you had to actually solve the problem. Okay, I'm not going to tackle that problem the purple way because I don't want to spend my time solving a system. I'm going to tackle it using the red method. Let's say that I started off the problem the exact same way, that I'm going to allow x to represent the first number. This is where I made the comment that I can work a little hard at the beginning. Rather than me just to default to, well, then the sum of their two numbers is 13, so let's make the other number y and write x plus y equals 13, I don't want to introduce a second variable. But I can use what I circled in red to write the second number in terms of the first. If the two numbers add to give 13, then if I take the total 13 and I minus the first number, x, that is the second number. You'll notice that that second statement that I wrote is no longer a let statement. I'm not letting something represent something else. It's a then statement. If the first statement is true, then the second must be. And you'll notice I didn't introduce another variable. So I'm not going to have to solve a system. I just took care of the first half of the first sentence. The two numbers have a sum of 13 by creating my then statement. What I could now do is the second half of that statement, their product is 42, and I could jump straight into, therefore, one number times the other one is 42. And now you'll notice I have an equation, but it only contains one variable, which means I don't have to solve a system. I can just solve an equation that I've solved hundreds of times. So for me now, I'm just going to write a little star, and I can just say solve, because really I'm just solving that equation as I have many times. Okay, just so that you don't think I'm pulling a fast one here, I'm going to go back to something I said I wasn't going to do, and I'm just going to go a little further. Can you take a look at the bottom of the purple solution? If you were to go through and solve that equation, I imagine most people would take equation 1 and get rid of either the x or the y. Like you might get rid of that x and say to get rid of a plus x, you're going to minus x. So you would rearrange equation 1 to solve for one of the variables, and now you're going to use substitution to sub that equation into the other one, and you'll notice my blue equation matches up with my red. So when you take a look at that problem from an overview, the purple, we didn't really think too much at the beginning. We just used x and y, default, and then translated. It left more work. The red, we actually looked at the relationship between the two numbers and didn't default to a second variable. So we did a little bit of work early, but that's going to save us some time later. Okay, there are your two ways to translate problem 1 to turn it into something useful to be able to solve. Okay, I think now that you've seen that for today, you can see what we're going to be doing in today's lesson. What I'm going to do is I'm going to throw a bunch of problems at you. We are going to translate them into something useful, make a statement about what we would do to solve it, and then we're moving on. Okay, let's jump into that next problem. So take a look at problem 2. Problem 2 is going to say two numbers have a difference of 10. What are the numbers if their product is a minimum? Okay, this is going to be the last problem that I'm going to go through right from the get-go with you. And then I think after this, you're going to be good to try some problems on your own. Okay, why do I want to walk through this one as well? Because I want to highlight something. We're going to try to be as efficient as we can be, which means we're not going to default to 2 variables. So we're going to try to use 1 variable. So when I read that problem and it says 2 numbers have a difference of 10, well then I could say, well, if I'm talking about numbers, I'm going to let, and I'll just be boring, let x again, represent the first number. I'm not going to let y represent the second number because, again, we're trying to avoid 2 variables. If the numbers have a difference of 10, then if x is the first number, then x plus 10 is the second number. Okay, if that caused a bit of a hiccup in that translation, let me just use an example. If 1 is the first number and the numbers have a difference of 10, then the other number could be 11. That would be 11. There's your 2 numbers. 2 numbers have a difference of 10. Now, I also want to highlight something right now. It really comes around the definition of first. Like when I call x the first number, am I talking about when I count? So I'm counting up. If that was the case, then those red numbers would be an example. But I don't know if there's any real, knocked down, nailed down definition of first in this instance. So, to make sure we're good, if 1 was the first number, the other number could have been -9. Notice 1 and -9 are 10 apart. So, I'm hoping you can see there's 2 different directions that you could have went. My red numbers are going to match my purple statements. However, I could have said x minus 10 as the second number, and that would have given me the green numbers. Either of those are good. Either are fine. There is no correct answer. Not really. I would argue maybe the purple, but that's something separate. Okay. I'm going to work through on the purple statements. Of course, you could have had that old green one. Okay. We've just used up the first sentence to define our numbers. That gave us our let and our then statement. Now I'm going to use that second sentence. What are the numbers if if their product is a minimum? Well, product means multiply. So I'm going to take the first number and I'm going to multiply it to give me the second. Where we could struggle a little bit is we're going to want to say that's equal to what? Like the problem doesn't tell me that the product equals 126. The product equals 12. It doesn't tell me what the product is. I have to find the numbers if the product is a minimum. So that's what I'm really looking for, a minimum. Okay, I want to walk back a little bit from this because I want to make sure that we do not make a mistake. And really, it's just a mistake in the situation we're in. I am going to call that function a P function. And the reason I'm going to look back up to the question, because it asked me for when the product is a minimum. So I'm going to use P for product. Now, I'm going to have some people that are going to look at that and go, but wait a second, you said don't use 2 variables, and now I got another variable in there, the P, and what? Hold on for a second. Can I get you to look up at the red and the green numbers that I wrote earlier? because I want you to notice something. There are infinitely many pairs of numbers that have a difference of 10. I just wrote 2 of them up there. 1 and 11 and 1 and -9. Notice, if I took 1 and 11 as my pair, that would give me a product of 11. 1 times 11. But I could have also had like 2 and 12. Those two numbers are 10 apart. That would give me a product of 24. If I took my green ones, 1 and -9, then that gives me a product of -9. Now can we look back up and understand what the question is asking? The problem wants me to know or to find the pair of numbers that have the smallest possible product, where the product is a minimum, right? The smallest. So notice, I'm creating all of these different possible products of numbers that are 10 apart. I am creating a product function. So what I have here in orange is the product function. Now, I'm going to do something. I'm going to just take that orange and I'm going to expand my brackets just so we can see something. What you just created was a parabola. You maybe see it a little bit better when you see it in that final orange form. You can see your squared. I don't know, if I even went back up to this line where it was factored, I'm hoping you can see your roots. So what I'm going to do is I'm going to shrink this down and I'm going to hop off onto the side for a second, just so we fully understand what we're doing. What I just did in orange was I just created my function. If you scan at that factored form, we should be good to see that you have a root at 0 and a root at -10. Your parabola has a positive leading coefficient, so it would be opening up. And if I was just to sketch something very crude, like I don't even know where the vertex is, other than the fact that I know I have to be halfway, I get something like that. What I want you to focus in on is the fact that what I have in orange represents all the possible products of two numbers that are 10 apart. So in order to find a minimum, I need to build a function. So can we take a look back up in the problem? You'll see that I circled the minimum. For me to find a minimum product, then I need to build a product function. That's what I did in the orange algebra. Okay. We should be good then if I just get rid of that little green arrow so we don't get distracted. We should be good to be able to find a minimum. Now, back when we were going through and we were sketching parabolas, or we were going through and we were changing into vertex form, I kept asking you to write something down. This is why it's important. My next line is going to say, for my minimum, because I can see my parabola is going to have a minimum, it's opening up, I know that my x has to equal negative b over 2a. And that should look very familiar to you. Now, you don't have to write down the negative b over 2a, just as we didn't back in that unit. You can go through and just calculate it. It's the negative b value divided by 2 times the a value. So there's our negative 10 divided by 2 times our 1. Now I can go ahead and I can simplify that, and I see that my x value is my negative 5. And you just get a little confirmation, of course, that x value is the x value at your vertex. That's what we're finding in this application. So I went farther than what we would need to do in this problem. Okay, I went farther in this solution because remember, today is just translating. We're not actually solving. But I wanted to make sure that we were good, that what you were creating in the orange isn't an equation in two variables. Not like what we did in the example 1. What we're doing is we're building a function in this situation because we need a function to find a minimum. Look on my graph one last time to make sure we're good. When I now label my axes, I think that that should make sense. My x-axis is still x. That's my first number. My y-axis is no longer a y-axis. It's a p-axis for product. So I built the function that represents all possible products. The problem asked me to find the one that would be the minimum product, and I know that all maximums or minimums occur at the vertex. So that's what I'm finding. Okay, I hope that that really gave you a good context to that this isn't two variables. Not really. You're building a function, not a system of equations. So what I want to do now is I want to get rid of all the stuff that wouldn't be needed. I'm going to get rid of this whole picture. I'm going to get rid of these possible products. I'm going to go all the way back, and I'm going to come to that point. When I ask you to translate, then I'm going to ask you to build the equation of the function. You can, if you wish, expand your brackets and collect like terms. That's actually pretty straightforward. But now what I want you to do is just make a little star at the end. And then what we're going to do is we're going to say what we would do. And you can just write, hey, you're going to use x equals negative b over 2a to find the vertex. Leave it there for the translate day, and we should be good. Make a note. Do not just write negative b over 2a. I think it's very important for us to remind ourselves that that negative b over 2a does not give me the product. No. It gives me the x value where that product occurs. So make sure that we're stating the x equals, and you are good. Okay, I think that's the big walkthrough part for us for today. We noticed in the first example, we translate it, we happen to get a system. Or we translate it and we get an equation in one variable, we solve. In the second problem, we needed to create a function in one variable. So I did that right away. Then we would use our negative b over 2a for our x value to be able to go through and find the vertex. Okay, the rest of the day today, I want us to make an attempt on trying these on our own. Okay, let's jump into that next problem. Okay, you can see problem 3 up on the screen, and we are ready to attempt them on our own. So what I want you to do is to go ahead and give that one a shot. Remember, we are not actually solving the problem. You are just translating for today. So you get to the point where you've created an equation and it's ready to be solved. Stop. Or you create a function and you are ready to find something on that function. Stop. And then we should be good. Okay, pause the video now. Give it a shot. Okay, we're back. So you take a look at problem 3. Two integers differ by 8, and the sum of their squares is 130. Find the integers. So if I have to find the integers, then I might as well go through and say I'm going to let x represent the first integer. And if I allow x to represent the first integer, and I see that they differ by 8, then I have one of two choices for the other integer. You could have said that it was an x plus 8, similar to what we did before, or you could have said that it was x minus 8. Really, it's your definition of first. I am going to continue following along with first means the smallest. So when I go through, my second integer would be me adding to it. X plus 8 then is the second integer. But remember, you are totally good if you have the orange. Okay, I'm going to get rid of the orange. There's my first step. I have now defined my integers with expressions. You have to include let statements. It's a must. If you don't, I have no clue whether your equation is correct. Okay, now that you have that, we can now take the second part of that sentence. The sum of their squares is 130. So I'm going to translate that exactly as written. The sum means add, their squares. So take the first thing and square it. Take the whole second thing and square it. Is means equals, and there is your total, 130. The sum of their squares is 130. There we go. Okay, you take a peek at that, and you can stop there for today. What I want you to do, though, just kind of be conscious that what we would now need to do is expand our brackets. And I'm hoping that we can see that when we expand those brackets, we're going to end up getting x's of different degrees. Like, take a look at that second term. When you expand those brackets, you're going to get some x squareds and you're going to get some single x's. So when we collect all of that stuff, we won't be able to collect into one variable term. That means that after we expand, we are going to look to standard form and then factor or formula to be able to solve. Now, one important point, when we actually get to solving these problems, the problem did say integers, and integers are whole numbers, positive or negative. So I'm hoping that maybe we can see we will be able to factor that problem to be able to solve. But maybe that's a consideration for a later date. Okay, you give me the purple and you are good for translating. Okay, let's keep it going. Let's tackle some more problems. Try to do as many as we can to be exposed to as much as we can. Okay, you see problem 4. You do not need any preamble from me. You should be good to attempt this one on your own. Pause the video now. Okay, we're back. So, two numbers have a sum of 24. Find the numbers if the sum of their squares is a minimum. Okay, we're dealing with a number problem again. Two numbers have a sum of 24. So I could say let x represent the first number. And if they have a sum of 24, then that means they total to give 24. So therefore, 24 minus the other number is the second number. Now, if there was any part, we goofed up on that one. Oh, I had x plus 24. Like, we treated it as if it was a difference. Keep in mind, y could have been our second number. And therefore, our equation could have been the first number plus the second number is 24. And so, if you want to get that y all by itself, so you don't use a second variable, then 24 minus x is the other number. So just to keep that in mind, if we're not quite up to the one variable thing at the get-go, Okay, I have now used that purple sentence, my first sentence, to create my let and then statement. Now I'm going to use that red sentence to build an equation or a function. The question says, find the sum or the numbers if the sum of their squares is a minimum. There's that word again, minimum. So if I'm looking for a minimum, I need a minimum of what? And I'm looking for the sum of their squares to be a minimum. So if I need the sum of their squares to be a minimum, then I need to build a sum of their squares function. So I'm going to call it S for sum of squares. And I'm going to build that function. Okay, well, if it is the sum of their squares, then I need to find the sum of their squares. So I need to take the first thing, square it, and add it to the second number squared. And if you take a peek at that red function, you'll notice it satisfies that second sentence. It is a sum of their squares. So what you have in red then is all the possible sum of squares of two numbers that have a sum of 24. It's all possible sum of squares. What we're looking for is when that one has a minimum. So I would like you to put down a little star for what you would do next. We have translated that problem correctly to build the purple let and then statement and build the red function. Let's just get into the habit. What would you do next? I hope we're good that we would expand all of that, put that in standard form, and since we were looking for a minimum, we know minimums occur at the vertex, and then we're going to use the fact that our vertex occurs where x equals negative b over 2a to start to get that ball rolling. Nice. Okay, we just translated another problem, and you've now had an opportunity to try two problems. One where you built an equation, one where you built a function. Hopefully that gives you a gauge of where you're at. Okay, I want to work our way through a few more problems today. Let's jump into the next one. Okay, you take a peek at problem 5, and as I said, you are ready to try them on your own. So I want you to pause the video now. Okay, we're back. Now, you notice when you read problem 5, it says a rectangle is 4 centimeters longer than it is wide. If its area is this, find the dimensions. You should love it when you have a problem that includes a shape. I do not think that there is anything wrong if when you read a problem, your reaction to writing a let statement is, oh, really? Do I have to? Yes, you have to. But what I'm talking about is, I don't think it's that bad of a thing to find it annoying, to not want to. Like, I don't like writing let statements. They're required because we have to define a variable, but I find them to be a pain. So when we see a measurement problem, a problem that includes a shape, we should love it because you can define the variable by just drawing a diagram and labeling it. So you don't have to use a let statement on this one. The problem says a rectangle, so I drew a rectangle. If I label part of that rectangle with a variable, your reader should understand what that variable represents. If they don't, that's their problem. So what I'm talking about is, if I said that I was going to call the width x, then your reader should be able to look at that diagram and be able to tell that this dimension is now called x. That's pretty plain to see. So I'm just going to clean up my diagram. There we go. Now, the problem says, the first sentence says, the rectangle is 4 centimeters longer than it is wide. So if x is the width, then my length has to be x plus 4. Or 4 plus x, same expression. Okay, that is one possible diagram. Okay, you could have also, though, drawn your diagram and said the length was x. If that was the case, then x minus 4 is your width. And I hope you notice that the purple and the blue don't really add any difference. Like really, whether you choose to start with the smaller and build, whether you choose to start with the larger and shrink, no difference. That's not going to have any impact on you. However, there may be some times where there would. I want to change that first sentence for a second. And I just want you to notice, say the question had said that a rectangle has its length being double. That's a really bad double. Double the length of its width. My first diagram works really well. If my width is x, then my length is 2x. My blue diagram isn't as easy to work with. If I now call my length x, my width would be x divided by 2 or 1/2 x. Ugh, now I got fractions. Doesn't mean you shouldn't be good with working with fractions. We should absolutely be good with it. But it doesn't mean that you want to include them. So a little piece of advice that I would give. Try to let your variable represent the smallest thing. That way you just build up towards it. And if you have the ability to avoid fractions, you generally will. So my advice to you would be, I think the purple is the better of the two. That's all. Okay. We have that as our diagram. Your reader should be able to see clearly what x represents. The second sentence says that its area is 192 centimeters squared. So I can build an area equation. It tells me specifically one dimension times the other dimension is 192. And there is your equation. You are good. I'm just going to clean up that 9. You are done for translating. Okay, couple key things. First off, we would write a little note that we would now expand. You'd put it in standard form. We should see we're going to get different x values and different x terms and x squared and a single x. That means we're looking to factor or formula to solve. Next thing, in terms of a little bit of a note, do not put units in your equation. I understand that if you're sitting in a science class right now, your science teacher may be barking at you to always include your units in your sentence. Don't. We should be quite comfortable to be able to recognize that that purple equation represents units in centimeters because of the first statement. We should be good to recognize the 192 represents centimeters squared because of the second sentence. Don't put units in your equation. Yes, science classes do. Math students don't. We could just tell that when we go through and solve in the end, we're talking about centimeters. Okay, hopefully we were good with translating problem 5. Same thing, I got 2 more problems to work through. Here we go. You should be good to be able to give problem 6 a read and try it on your own. Okay, pause the video now. Okay, we're back. So you notice the problem says the hypotenuse of a right triangle. So we got a shape again. So I'm going to draw a quick sketch of my shape. It says it's a right triangle. There is my right triangle. So I now have to go through, and it says that the hypotenuse of that is 10 centimeters. So maybe what I do is I just label on my 10 centimeters. Now my second sentence says, one of the other two sides is 2 centimeters longer than the third side. Okay, one of the other two sides is 2 centimeters longer than the third side. Well, what I could do, if you follow my advice from before, I'm going to make my smallest side x. I don't know what it is. That makes the side that's a little bit bigger than it x plus 2. Like I said earlier, you could have said, I'm going to make the bigger side x, the other side would be x minus 2, wouldn't really cause a problem. Both of those are good. Okay, if I just go with what I have in red, then the question now says, find the unknown side lengths. And you'll notice it didn't give me anything in the problem that told me what equation to build. Okay, it actually did. And this is what we have to be aware of. You are responsible for understanding all the relationships that you've been exposed to in the past. This one you've been exposed to for a number of years. So even though it doesn't explicitly state it in the problem, it does tell you that that shape is a right triangle. And you know how the sides of a right triangle relate to each other. Yes, we have good old Pythagorean theorem. So you know that the sum of the squares of the two smaller sides has to equal the square of the largest. There is your good old a squared plus b squared equals c squared. And there we are, done for that problem. Yes, I want you to write a little star, make a little note that you would expand all of that. We should see we're going to get x's of different degrees, so we are looking to factor or formula to solve. There we go. If you got down to that one, outstanding. Okay, one last problem that I want to work on translating for today. Okay, you can read problem 7 on the screen. Old MacDonald. I want you to work your way through, give it a shot. We'll come back and we'll check and see how well we're doing. Okay, pause the video now. Okay, we're back. So we've got Old MacDonald wants to enclose a rectangular field with 200 meters of fencing. Okay, so it's like he has this big field, open field, and he wants to put, it's a rectangular field, and he wants to enclose it. So he wants to put up some fence in the shape of a rectangle. But what he wants is he wants to make sure that the area of the field is maximized. So he wants the biggest amount of space inside that rectangle as possible. He knows he has 200 meters of fencing to go around. Okay, if you were a little unsure what the problem was asking you, I think what I just walked through could have clarified. So you have another opportunity to pause the video now and try this one on your own. Okay, otherwise, you're coming along with me. So if I just get rid of my crude little sketches there, I now have to try to build a rectangle that I know all the way around on that thing is 200 meters. So I could already say, well, I know that I've got a length and a width of a rectangle. And since you gave me 200 meters all the way around, that's my perimeter. And I know that my perimeter is 2 lengths plus 2 widths. Nice. Okay, but the question also asked, I need to maximize the area. Well, I know that the area of that rectangle is length times width. Okay, so which one of those things am I going to use? Okay, here's where I want to now go. That was me stumbling. Me acting like I didn't know where I was going. And all I did was just write down everything I knew about rectangles. Okay, I want to now tackle this problem like it has a purpose. And I've got some skills. Not that I know where I'm going. I'm still going to stumble, but I'm going to stumble in a guided way. Okay, I'm going to get rid of all of that stuff that I just drew down or wrote down. And now I'm going to tackle this problem the way I might want to. Okay, let's focus in on the red. The problem asks me to find an area that is maximized. If I'm going to maximize the area, then I need to build an area function. My problem is me writing L times W creates my function in two variables, L and W. I can't have that. I need my function to be in one variable so it represents an area function where I could have a parabola and I could find the maximum value. So having both L and W there isn't good. That means I need my length to be written as a width or my width to be written as a length. So I come back to my diagram. If I just call that W and that L, that's my two variable problem. So what I want to do is I want to write one of those other dimensions in terms of the other. So let's just say that I start the problem and I say, I'm going to call the width W. Now I need to be able to write the length in terms of width. Okay, how can I do that? I want you to listen to my reasoning very carefully. If I have 200 meters to go around that entire shape, that's my fencing, that's my perimeter, then I know 200 is my total. By me calling this one side W, I actually called the other side W as well. So if I was to put fencing down both of those W sides, I would have just used up 2 W's worth of fencing. Look on the bottom. That's the amount of fence that I have to put on the length. 200 minus 2 W's. If I take my 200 minus my 2 W's, then that's going to leave me with fencing that I have to put on both of those sides. Right? I need to enclose that rectangle. But my dimension I'm labeling on the bottom is only for one side. So I need to take that amount of fencing and I need to divide it by 2. Now, that just represents what's left over for the red side. Okay, I'm going to erase that bottom, fix in my rectangle. I am now going to simplify that. If you notice on that dimension, if I just zoom in a little bit to make it a little bit bigger, I could divide a 2 out of both of those terms. And so I could simplify that to 200 divided by 2 minus 2W divided by 2. I could divide the 2 out of both. There's my 100 minus W. Okay, I'm going to get rid of those purple arrows. There we go. That's my other side. Okay, that could have been confusing for some people. And that's okay if it is. But I really want you to work on that reasoning. It's the total I started with minus what I used up by labeling my W. Then break it apart, divide it up into how many sides I need. Okay, what if that is a real struggle? And I'm not talking about a struggle today. It should be a struggle today. But what if that's a struggle 2 weeks from now? How can I get that dimension on the bottom? I'm going to tackle it the long way. I want you to imagine that I use that 2 variable thing we know we can't use. Well, I'm going to go back to my orange 200 meters of fencing. I know that that is the perimeter of a generic rectangle. So, if I have a perimeter of 200, then I can sub it in. Well, now, since I know I can't use that orange L, I need to rewrite that L in terms of W. I'm going to take my orange equation and I'm going to rearrange it to solve for L. That means let's get rid of the 2W. And now I have to get rid of my divide by 2, which means, my times by 2, which means I am going to divide by 2. When I take a look at my equation, for me to get rid of my times by 2, I need to divide it out. And when I divide it out of everything. That is going to allow me to simplify that my length should be 100 minus W. Hey, there's the same blue dimension we got just through reasoning. Okay? I don't want you to use the orange. I really want you to try to reason that out. But if you are absolutely stumped, then feel free. You can use the orange. Just try to work your way away from it over time. Okay, I'm going to get rid of it off of our screen because I don't want it to be there. I want us to just be able to work through the blue. Okay, why do I love those blue labels? Because now I've labeled both sides of my rectangle using the same variable. So now if I jump back up to the red and I said I'm going to take one dimension and multiply it by the other one, now my area function is in terms of one variable, W. So I'm hoping we could see. You could go ahead and expand that if you wanted to. There is my area function. But we should all be good that since the problem asked you to find a maximum, you would now need to take that and use W equals negative B over 2A to start to find the dimensions that maximize the area. Okay, there was our last problem for today. And I hope you can see we covered a wide range of problems. Well, really, it's hunkered down to 2, but in a bunch of different ways. We solved a couple number type problems today, or at least translated them. And we did the same thing with some measurement, working with rectangles, right triangles. Okay, like normal, your job, jump in and get some practice. If you are comfortable to translate, then all of these problems just become about mechanics. So you would be clearly comfortable to finish them all off. That should be confidence boosting. If we're struggling on the mechanics, then maybe when you're done translating these problems, you want to hop back and start working on some of those mechanical issues. So when we actually get to solving the full problem all the way through, you're comfortable with all aspects. Okay, jump in and get some practice. Best of luck.